In this example problem, we're given a small frame that's supported at at 3 points, and we're asked to determine what is the magnitude of the components of the applied force at point B of 300 pounds or 300 newtons, and we want to determine what components of that force are parallel with member AB and uh, uh, what what's the magnitude of the component that's perpendicular to AB. So you want to determine the force that is parallel with AB, and you want to determine the force that's perpendicular with AB. Okay. So to do this, we're going to use the dot product. So the first thing we need to do is we're going to solve for UAB. Okay, so UAB we know is equal to RAB divided by the length of RAB. Alright, we know that RAB is equal to RB minus RA. In this case, point A is at the origin, so RA is going to be equal to 0. So RAB is just going to be equal to RB. And RB is equal to 2 meters in X. It's equal to 6 meters in Y. And it's equal to 3 meters along the Z direction. Okay, so if we divide, so we know that RAB is equal to RB. The magnitude of RAB would be equal to the magnitude of RB, which would be equal to the square root of 2 meters squared plus 6 meters squared plus 3 meters squared. So I'm just going to take the squares already. So that ends up being 49. So square root of 49 is equal to 7 meters. All right, so we can say that UAB would be equal to we'll have 3 components. That would be equal to the x component of RB divided by the magnitude of RB, the y component of RB divided by the magnitude of RB, and the z component divided of RB divided by the magnitude of RB, which will give us 2/7, 6/7, and 3/7. Okay, all the meters will cancel out, and we'll be left with our unit vector, which should have no units. So once we have UAB defined as a vector, we can take the dot product. So we know that the force that is parallel with UAB is equal to the dot product of our force times UAB. Okay, so we know that the dot product between two Cartesian vectors is equal to the x components multiplied together, so it would be equal to f of x times 2/7, which is the x component of UAB, plus f of y times 6/7, which is the y component of the unit vector UAB, plus f of z times the unit vector of along the z direction of UAB. Okay, so for our given force, it actually only has a single component. It only has a component in the y direction. So because of that, f of x is equal to 0, and f of z is equal to 0. So the only thing we're left with is 300 newtons. Okay, so if we plug that in, what we get for our parallel component with UAB, we get 300 newtons times 6/7, so that's equal to 800 newtons divided by 7. All right. So that's about 257.14 newtons, or 257 newtons. All right. So to determine the perpendicular component of UAB, we can take the square root of our total magnitude of our vector, which is equal to 300 newtons squared. So this is just the total magnitude of vector F. All right, and we're going to square that, and we're going to subtract it. We're going to subtract the parallel component. So we're going to subtract 257.14 newtons squared. All right, if we evaluate that, we end up getting 154.52 newtons, which is about 154 newtons. All right. So just to recap what we did, we first solved for our unit vector UAB using the position vector RAB and its magnitude. Once we had the position vector, or the unit vector UAB, we then took the dot product of UAB with our force vector in order to get the parallel component of the force along member AB. Once we had our parallel component, we could then solve for the perpendicular component using the square root of the magnitude squared, or total magnitude of the force squared, minus the parallel component of our force squared. All right. And that concludes this example problem on how to find the components of a force along a line and perpendicular to the line.